Today we're going to talk about something called cosets. Now, you're familiar with the word sets. A set is just a collection of some stuff. The idea behind cosets is you create a bunch of complementary sets. And I like to use an analogy related to laundry. So if you're like me, you tend to have a pile of clean laundry sitting around, and when that pile hits some sort of critical mass, you're like, you know what, I better put this laundry away. Now, most of us probably have some kind of organization system for our laundry. I have this little dresser here. And when I put my clothes away, I use an organizing principle that maybe you use too. You know, I have a sock drawer. My socks go in here. And then I have, like a t-shirt drawer. My t-shirts go in here. And then I have my pants drawer. Pants go in here, and so on. And I put my clothes away according to this principle. So I'm like sorting through this pile of clothing, which looks kind of big and frightening and disorganized. And I'm like, aha, a sock that goes in the sock drawer. And there's some pieces of this analogy. I know it's a sort of weird analogy to throw at you in the middle of your, 300 level abstract math course, but bear with me for a sec. So notice that I can't put one piece of laundry in more than one drawer, right? Like if I have a sock and I'm going to put it somewhere, I'm going to put it in the sock drawer, and that means it can't also be in the pants drawer or the t-shirt drawer, right? It just goes in the sock drawer. And I put my laundry away according to this principle, so things go in the drawers where they're labeled. And by the time I'm done with this process, I should have completely gotten rid of this pile of laundry. So I've put all of my laundry away in my dresser, which organizes it into these drawers that make it easy to find what I'm looking for. Okay, now in this analogy, the items in the laundry are our group elements. So we have a group, it's got some elements, and the drawers are going to be these things that we call cosets. Right, so I have one set that I use to create some sort of organizing principle, and then I have all of these complementary, that's where the CO comes from, sets that get formed by making the choice of which set I'm going to use to organize stuff. Oops, I don't mean for all of those to be plural, but you get the gist. Sorry, let me erase all those S's. So we pick a set. It's usually going to be a subgroup. And then we do something like divide by that subgroup, whatever that means, and that makes a bunch of remainder classes like we had in the integers, mod, whatever. And all of those classes become these things that we call cosets. And when we're done with that, instead of a clean floor, we have, I guess, in this analogy, a clean mind, because we know how the elements of our group are organized in some way that makes it easier to work with. So cosets help us organize our groups into sets that have some nice properties. And one of the weird, cool things we're going to be able to do is take this set of sets. So we take our dresser basically, right? That's our set of sets. We can define an operation on it. And then we can ask, is it a group? And that's what we'll be doing for the next few classes. We're going to be really interested in the question of how do we organize our group elements into these things called cosets, define an operation on cosets, and then check to see if this new object that we've created, the set with an operation, is a group. And if it is, we're going to call it a quotient group. The word quotient might remind you of division, and that's because this is modeled on how we made the sets z modulo n for some integer n. We took remainders after we divided by some divisor, and we made equivalence classes or remainder classes. And we saw that that forms, for instance, the integers are a group under addition, right? So we've got this big disorganized pile of integers, and then if we do something like divide by, let's say, 5, then we get z mod 5, which now, instead of a set with infinitely many things, is a set with 5 things. And if I think about how that looks in my dresser, so when I look at the integers, those integers are my group elements. So I have elements of the integers. And I want to organize them based on their remainder mod 5. And so the first organizing principle is 0, things that are divisible by 5. So that's an example of a set that I might use, the divisible by 5 set, and then everything else sort of falls out of that. I've got the remainder class 1, I've got the remainder class 2, I've got the remainder class 3, I've got the remainder class 4, and then I get back to, like my next thing that I would write down if I were just writing this down without thinking would be the remainder class 5, but that's also 0 mod 5. So I can organize the integers into this dresser by using division by 5, essentially. And we proved a bunch of stuff about the way that integers in these sets work. You can look back in our notes at, I guess it was way back in chapter 3. Remember, an integer can't be in more than one of these equivalence classes, so it's just like a sock. You're either in the sock drawer or you're not a sock and you're in whatever drawer you belong to. We also know that either two drawers are the same or they have an empty intersection, meaning that, if I find an element of clothing or an integer, and I'm like, oh, it has, remainder n and it also has remainder m, then n and m belong to the same coset, and so it really belongs to exactly one drawer. So I know this analogy starts to break down, especially when I start talking later about adding shirts and pants. That's going to be a little bit weird. But the big idea here is that cosets take these group elements and we add even more structure by doing some sort of organizing relative to a set. So we're going to figure out how to use our sets. Usually it will be a subgroup. So in Z, this subgroup that we have in Z is the set of all the things that are divisible by 5. If we think about why that's closed under addition, we have that two multiples of 5, when we add them together, give us another multiple of 5. It's not empty because 0 is a kind of silly multiple of 5. Associativity gets inherited from the integers, and if I have a multiple of 5, like 5n, its additive inverse is negative 5n, which is also a multiple of 5. So the equivalence class 0 mod 5 is itself a subgroup of the integers under the operation addition. Okay, let's get into the technical details. All right, we'll start the chapter with some definitions about how we're going to make sets in groups. So the first part of this definition, I have a subset A contained in G, and I have a subset B contained in G. And what I want to think about, I wrote B. What I want to think about is how to make a set that is, in some sense, the product of those sets. So if I wanted to do this, I could think about taking all possible products where A comes from A and B comes from B. And so, for example, if I look at the integers and I have the subgroup multiples of 2, let's make that A. So my group is G, and I have the subgroup generated by, let's say, 6. That's B. Then the set AB is going to be everything that looks like a multiple of 2 times a multiple of 6, right? So that's m and n in this case are integers. And so what we really get here, I meant set brackets here, boop, boop, boop. So what we really get here is the principal ideal generated by 12, right? We take 12 2 times 6 is 12, and then we multiply that by integers. So that's one way of thinking about how to multiply two different sets. And I used subgroups of G, and that gave us a nice answer that was another subgroup of G. Just something to observe. I can also do this with a particular element. So if I have an element G in the group G, and some set that I'm interested in, some subset S contained in G, then I could think of a new set that says take everything in S, so take little s in S, and multiply it by this special element G that I picked out. So I could also, we've talked a little bit about 2Z, which gives us, so Z is a subset of itself, 2 is an element of the integers, and this gives us the set of multiples of 2. So 2 times n, where n is in Z, which, again, that was the principal ideal generated by 2. I'm mentioning ideals here just because we're getting closer to the end of the course, and I want to bring in some of the older ideas from the course. But multiples of 2, perfectly fine subgroup under addition from the integers with the operation addition. The name of the set GS is called the left coset of S generated by G, and the left comes from which side we're multiplying the G on. And then we could also do right cosets. Because we won't necessarily deal with abelian groups, we're going to kind of pick the convention that we're going to deal with left cosets unless we really have to do right cosets for something. But if I don't mention left or right, just assume that I'm talking about a left coset. We can also then say, like, what are all the possible left cosets we could form from the group S? So if I think about this notation, which kind of looks like G divided by S, it's saying take the set S and then make every possible coset from it by multiplying on the left by all the elements of G. And we read this as G mod S, which is similar, so you might think back to our examples like Z mod 5 or Z mod 2 or things like that. So mod is taking on kind of a similar vocabulary role for us here. We also might want to ask the question, how many left cosets are there? So how many left cosets? And we have notation for that. Our notation uses the colon and brackets again. So G colon S is going to be the number of left cosets of S in G. So it's a size. Number of left cosets of S in G. Now, we've had a lot of experience in this course with this notation, right? We've seen, brackets, colon stuff all over the place. And in almost all of the cases we've seen these things, we've been able to set them equal to one another. So if you're using good mathematician psychology here, we're probably going to take this idea, the index of S and G, and we're going to try to relate it to, for instance, maybe one of our dimensions of an extension field, or the degree of a polynomial, or the degree of an algebraic element over Q. So this is going to come back. We use this notation over again because it's a really useful piece of notation that relates these big ideas in the course for us. I'm going to let you take a look at the examples in the notes from class. They are pretty nicely done. The first example here, right here, boop, 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 goes through and finds the left cosets of a subgroup of the permutations of 3 elements, the group of permutations of 3 elements, and it works out what the left cosets are. And it turns out that there are only 2 of them because a lot of them get redone, and that kind of makes sense. So I'm not going to go through all of the multiplications here. I'll let you practice those permutation multiplication, cycle multiplication, but I do want to go through this little section of notes here. S is a subgroup it's got 3 elements, and when we multiply through by the various multiples, or by the various elements of S3, we find that we get a set back that has 3 elements in it again. So each coset has the same number of elements. Part A is saying same size. In our dresser analogy, that's maybe a little weird. That's saying I have the same number of socks as shirts, but just go with it. I mentioned previously that the cosets are either equal or disjoint, so there's no overlap between 2 cosets. Which means once I figure out what coset the element 132 belongs to, that's the only one it could possibly belong to, right? There's no other option. And so, in particular, I also found that when I found it up above on the previous line, when I multiplied by 1, 2, 3, I know that that's the only possible coset that's going to contain 1, 3, 2. So these 2 elements right here are actually the same coset. We also see, so part C here is saying that the permutation group can be written as the union of its cosets. So basically, in our laundry example, it's saying if I dump out all of my laundry on the floor, I get my pile of laundry again, and I haven't lost anything, and I haven't added anything. So this is, and in fact, we could say it's the disjoint union of its cosets. The disjoint piece comes from part B. We've also got part D, which says that, what does part D say? It's saying that when I multiply certain things, like when I multiply by inverses, I get some things that are in S and some things that aren't in S. And another piece to notice here is that there are 3 elements in each coset. I'm supposed to get 6 elements in my group when I dump my cosets out, and that means that I'm going to get exactly 2 cosets at the end of the day. This slide has another example. We're looking at a subgroup in the group Z mod 6. Our subgroup is 0 mod 6 and 3 mod 6. We've got a little operation table to show that it is in fact closed under addition, and because we're working with finite subgroups, that's all we need. We've got the H as a subgroup of Z6. Then we want to think about how we write down a coset when we're working in a group whose operation is addition. And so you'll notice on the slides here that we use addition to write n mod 6 plus H. This addition in here comes from the group operation. So this is whatever our group operation is, that's what we're going to use to write down our cosets. So this is our group operation. And you might also think to yourself on the previous slide where we had A contained in G and B contained in G, if G is abelian, which means we usually write it as a group under addition, so we think about its operation as addition, then instead of writing down A times G, we would write down A plus B. Sorry, I said A times G before I meant A times B. And we get A plus B looks like all the possible sums of elements. A from A and B from B. So it's good to keep in mind what your group operation is, because if it's addition, you're going to use addition to write these sets down. If it's function composition, and we use function composition to write it down, maybe there's some weird group out there whose operation is exponentiation, and then we would use exponentiation to write these things. That would be like A to the B or something like that. But the group operation comes along for the ride when we are making our cosets. Here, we make some observations about the way things work out. They're similar to what we noticed before. Every coset has the same number of elements of our set S, which is, in this case, S is equal to H. The cosets either are equal or disjoint. Z6 is the union of all of its different cosets. We find that we have exactly 3 cosets here. We have the coset H, the coset 1 plus H, and the coset 2 plus H. And then part E is telling us that since we're working in an abelian group, it doesn't matter if we do right cosets or left cosets because addition commutes. So we're going to get the same thing on either side. Here's one more example. I'm going to let you go through this one on your own as usual. Put your questions on Piazza. I hope you'll have lots of questions about this stuff. It's not the easiest stuff that we've done in the course so far, but it's super important. And finally, we have a proposition about the way that cosets behave if we take S to be a subgroup of a group G. So proposition 20.4 takes into account what those different observations we made before say, and it proves them in general. So part 1 says that there's either they're going to be cosets are this like two cosets are equal or disjoint. There's no overlap between distinct cosets. And you can compare this back to chapter 3 stuff where we talked about equivalence classes modulo some integer n. Right? Two equivalence classes are either the same equivalence class or they don't have any element in them. We did a proof of that on Overleaf as a class, so we've also got the Overleaf proof for this result in chapter 3, which is going to be really similar to the way that the proof of 1 goes before. You'll see that we're using that little logical equivalence. P implies Q or R is logically equivalent to P and not, I guess in this case, R implies Q. And the proof really, if you think about it using multiplication instead of addition as the operation, the logic of the proof is exactly the same. Similarly, we proved something like 2 for integers mod n, but we proved it with subtraction. So in the integers mod n, we said that A mod n equals B mod n, if and only if, I'll write it B minus A, let me write it as negative B plus A, is in 0 mod n. That's an additive way of talking about what number 2 is saying. It's saying that these two cosets, xs and ys, are the same if and only if you take x, you multiply on the right by y inverse, and you get an element of the set S. And that's the logic that goes behind that proof. There's a nice little piece, a nice little trick for working with cosets embedded in that proof, which is that the identity is always in S. So this is kind of a nice hint to keep in mind when you're working with these things, which means, for instance, that we could write the identity. What's helpful to use here? I guess it's helpful to write it as, in this case, we write the identity as maybe y times y inverse, right? So that's an element of x, or something like that. It's really nice to be able to use that the identity is in our subgroup. So be creative with using the identity. Right? This is like the first time you saw us use 0 plus 0 equals 0, or 1 times 1 equals 1 in class. That's the same kind of trick we're using here. Part 3 up here is a little bit hard to parse, but all it's saying is that G is the union of the cosets of S, mod G, the cosets of S over G. So we take all the cosets, we put them together, and we get our group back. And then part 4 says if we have a finite subgroup of our group G, so if the size of S is less than infinity, then all cosets have the same size. There's one more example down below. We're looking at a subgroup of S6. We are saying that the permutation 1, 2, 3 and the permutation 2, 5, 3 are both in S, and we want to use some of the stuff from Proposition 20.4 to show that these two cosets are equal. So 124s is equal to 14 times 25s. The two proofs below use different parts of 20.4. One of them uses 20.4 part 2 that says that they're equal if and only if 1425 inverse, the inverse of that permutation, times 124 is an element of S. Well, we get that thing, that their product will give us 253 inverse times 123 inverse. Since 123 and 253 are both in S, their inverses must be 2, and it's closed under multiplication. So this line right here, when we work all of this out, gives us, by Proposition 20.4 part 2, that these cosets must be equal. We could also look for an element in common to both of those cosets and use 20.4 part 1 to say that since they have an element in common, they must not be disjoint, which means that they have to be equal. The way that this proof proceeds is by showing that the element 1423 belongs to both cosets. So we write it as an element from S, 123, times the element 124. Now 123 is an S because it's 132 inverse. And 124 is the thing that we're using to make our coset. Similarly, we write 1423 in here in the other coset that we were working with. So they have an element in common, and Proposition 20.4 says they must be equal. So there are lots of ways to work with cosets. We're going to work with cosets quite a bit from now to the end of the course. And the big question that we want to ask and start to get an answer to is what kind of special subgroup makes it so that our set of cosets, so the set of all possible left cosets that we could make from a set S, is itself a group under that operation we made on sets before on the first page, second page of notes.